Hello guys, Sir DV again to give you a continuation on the iterative method I discussed last time. And comparing them with the direct method, the iterative approach is much more faster in terms of convergence because of the lesser or the fewer elementary row operations needed, no, to perform the procedure, especially for sparse matrices which are diagonally dominant. Okay, for the next procedure or iterative procedure, we have the Gauss-Seidel method, which is almost the same. Actually, very much similar. It is a variant of the Jacobi method. Okay, so this is very much similar with the Jacobi because the uh, form uh, using the fixed point iteration. Okay, and the advantage uh, of Gauss-Seidel with Jacobi is again this has even a fewer number of operations needed since we are using the new the new values of xi's instead of the old values. No? So the convergence is faster because in nearly all cases the new values are more correct than the old values. So if we try to take a look at at this procedure here, um, on the first iteration, we come up using x2 and x3, or sorry, the second iteration to be 0, upon which we get a new value, a new value for x1. So what the Gauss-Seidel is doing is that instead of using a, a, uh, a value of 0 here, we use the new value of 1.833 here, okay? While x3 is still 0, okay? So x3 is still 0 there. And when you're solving x3, you are now using the new value of x1 in terms of 1.833, and at the same time x2 uses your 0.714 as your new value. Okay, so this is now the new value computed uh, computed at the same or the current iteration. Okay, so hindi mo pa man nagamit na fulfill na natapos yung cycle, you are now introducing a new values for you to increase the speed of convergence. Okay, and so on and so forth on the third iteration, instead of using the first value here of 1.83, 0.714, and zero point 0.2 in this regard, I'm using now the new value. I'm using the new value to come up with a more uh, accurate, closer solution vector than the Jacobi method. Of course, these are erroneous values since we are taking different substitution here. These are not the true values that that I'm trying to solve because this is the Jacobi procedure that I'm showing you. But if we try to look now on the Gauss-Seidel solution using the same problem, the actual values will now be this one. Okay. The second iteration, you will see that the convergence is much more closer to the final solution of the system of linear equation, and And using the same approach, we substitute the x2 and x3 here in terms of these two values. Okay, but after solving for this, we will no longer use 1.83, but rather use 2.069 here. Okay, so we are updating the solution, a vector to be substituted on the equation as the procedure is in process. Okay, so it's actually a dynamic way of solving in real time the a solution vector by substituting the latest or the most updated value as the procedures goes. Okay, as the iteration proceeds, and eventually, if you will notice, after the sixth iteration, convergence is actually achieved. Okay, while in this is the Gauss-Seidel approach, but in the Jacobi approach, we need 9 iterations, okay, to fulfill or achieve the same accuracy. So we are actually 3 less not operation, but 3 less cycle. So fewer operations if we are doing row operations per cycle in terms of the number of rows to be equivalent to 3 times 3 or 9, excluding the row interchanges. Then we can say that roughly we have saved 9 times 3, 27 operations. And if we are doing large matrices, in structural engineering, we will be dealing with very large matrices. We are actually saving a lot of resources, time, and memory, no, for us using a more efficient way of solving systems of linear equation. And this is not yet the end of the line. We will be looking forward to some more efficient techniques that may supersede these methods after this presentation. So thank you very much for listening. I'll see you on the next video.